Hi friends, this is M. Sriram from CSA D section. Subject is Applied Physics, AIT Tech Talk. Topic is photon generation in forward based silicon PN junction. Photons are generated by forward basing of silicon PN junction at 10 to the power of minus 5 to 10 to the power of minus 4 quantum efficiency through radiative recombination at large distance from the forward based junction. Leakage current of magnitude significant for some LSI circuits can appear due to the substrate minority carriers generated by the photons. The effective decay length of the measured leakage current is about 700 to 1000 micrometers. The effects of forward basing an input node or a parasitic lateral bipolar transistor are therefore longer ranged than commonly assumed. Introduction. A PN junction is a boundary or interface between two types of semiconductor materials, P-type and N-type. Inside a signal crystal of semiconductor, the P positive side contains an excess of holes while the N negative side contains an excess of electrons. In the outer shells of the electrical neutral atoms, this also electrical current to pass through the junction only in one direction. The PN junction is created by doping, for example by ion implantation, diffusion of dopants, or by epitaxy, growing a layer of crystal doped with one of dopant on the top of layer of crystal doped with another type of dopant. If two separate pieces of material are used, this would introduce a gray boundary between the semiconductors that would severely inhibit its utility by scattering the electrons and holes. P-N junctions are elementary building blocks of semiconductor electronic devices such as diodes, transistors, solar cells, LEDs, and integrated circuits. They are the active sites where the electronic action of the device takes place. For example, a common type of transistor, the bipolar junction transistor, consists of two PN junctions in series in the form of NPN or PNP, while a diode can made for a single PN junction, a Schottky junction is a special case of PN junction where metal serves the role of the NP N-type semiconductor. A PN junction possesses a successful property for modern semiconductor electronics. A p-doped semiconductor is relatively conductive. The same is true of an n-doped and hence non-conductive depending on the relative voltages of the two semiconductor regions. By manipulating this non-conductive layer, PN junctions are commonly used as diodes, circuit elements that allow a flow of electricity in one direction but not in the other opposite direction. Bias is the application of a voltage relative to a PN junction region. Forward bias is in the direction of easy current flow. Reverse bias is in the direction of little or no current flow. The forward bias and reverse bias properties of the PN junction imply they can be used as a diode. A PN junction diode allows electric charges to follow in one direction but not in the opposite direction. Negative charges can easily flow through the junction from N to P but not from P to N, and the reverse is true for holes. When the PN junction forward biased, electric charge flows freely due to reduced resistance of the p-n junction. When the p-n junction is reversed bias, however, the junction barrier and therefore resistance becomes greater than and change flow in minimal forward bias. The panel shows energy band diagram, electrical field and net charge density. Both P and N junction are developed at a 1e 15 centimeter cube 0.0000116 C by centimeter cube doping level leading to built-in potential of 0.59 volts. Reducing depletion width can be interfered from the shrinking carrier mentioned across the p-n junction, which as a consequence reduces electrical resistance. Electrons that cross the p-n junction into the p-type material or holes that cross into the n-type material diffuse into the nearby neutral region. The amount of minority diffusion in the near neutral zones determines the amount of current that can flow through the diode. Only majority carriers electrons in n-type or holes in p-type can flow through a semiconductor for a macroscopic length. With this in mind, consider the flow of current across the junction. The forward bias causes a force on the electrons pushing them from the n side toward the p side. With forward bias, the depletion region is narrow enough that electrons can cross the junction and inject into the p-type material. However, they do not continue to flow through the p-type material indefinitely because it is energetically favorable for them to recombine with holes. The average length an electron travels through the p-type material before recombining is called the diffusion length, and it is typically on the order of the micrometers. Although the electrons penetrate only a short distance into a p-type material, the electric current continues unimpeded because holes, the majority carriers, begin to flow into opposite direction. The total current, the sum of the current and the whole current, is constant in space because any variation would cause charge built over time. This is Kirchhoff's current law. The flow of holes from p-type region into the n-type region is exactly analogous to the flow of electrons from n to p. Electrons and holes swap roles and the signs of all currents and the voltages are reversed. Therefore, the macroscopic picture of the current flow through the diode involves electrons flowing through the n-type region towards the junction, holes flowing through the p-type region in the opposite direction toward the junction, and the two species of carriers constantly recombining in the vicinity of the junction. The electrons and holes travel in positive direction, but they also have positive opposite charges, so the overall current is in the same direction on both sides of the diode as required. Reverse bias. Connecting the p-type region of the negative terminal of the voltage supply and the n-type region to the positive terminal corresponds to reverse bias. If a diode is reverse biased, the voltage at the cathode is comparatively higher than at the anode. Therefore, very little current flow until the diode breaks down. The connections are illustrated in the adjustment diagram. Because the p-type material is now connected to the negative terminal of the power supply, the holes in the p-type material are pulled away from the junction, leaving behind charged ions and causing the width of the depletion region to increase. Likewise, because the p-type is connected to the positive terminal, the electrons are pulled away from the junction with similar effect. The increase the voltage barrier, causing a high resistance to the flow of charge carriers, thus allowing minimal electric current to cross the p-n junction. The increase in resistance of the p-n junction results in the p-n junction behavior as an insulator. The strength of the depletion zone electric field increases as the reverse bias voltage increases. Once the electric field intensity increases beyond a critical level, the p-n junction depletion zone breaks down and current begins to flow, usually by either the Zener or a avalanche breaks down and current begins to flow, usually by either the Zener or avalanche reversibly, as long as the amount of current flowing does not reach levels that cause the semiconductor material to overheat and cause their terminal damage. This is the examples of p-n junction diode. Thank you.